Welcome everyone. In this video, we are going to discuss arrangements of letters on vertices of a cube. So you have a cube over here and that contains 8 vertices. You also have 8 letters, 2 A's, 2 B's, 2 C's and 2 D's. You are going to arrange these letters on the vertices. Now clearly, if you are going to arrange them in the actual way, then you permute like in 8 factorial ways and you avoid the repetitions. You don't want to permute the 2 identical A's or 2 identical B's. So you would go ahead and divide by 2 factorial 4 times. But that's not the case here. We make it more trickier. In fact, this question came up in our SuMON process. In the fortnight 29, this was a hard problem in level 3. So this one, the cube allows the rotation and it reads the configurations obtained through rotations as identical. It cannot differentiate, which means a configuration obtained through rotation of the other are considered equivalent here. So you have to merge those equivalent configurations. How are we going to solve this then? It is really impossible to write all the possibilities. There are a lot more in the permutations. Let's see how to get started with this. Think about the question before actually looking into our solution. Here is the problem statement and here is the cube. So there are 8 vertices, 4 in the bottom, 4 on the top face. The letters available are 2 identical A's, 2 identical B's, 2 identical C's and 2 identical D's. So you also have one more condition. The 2 A's that you are going to arrange must be on diagonally opposite corners of a face of the cube. So please add on to this condition. So if one A occurs here, then the other A will occur here. So they both must lie on the same face. So it's in the bottom face in our assumption. And consider 2 arrangements equivalent if one can be obtained from the other through rotation. Find the number of distinct arrangements of letters possible on the cube. At first, try fixing the positions of A. Suppose I consider the position of A to be in the bottom left corner and the bottom right corner. In the bottom face, the front left corner and the back right corner. These two are diagonally opposite and they belong to the bottom face. Why am I fixing it? Because however you arrange the 2 A's, maybe in the back face or in the front face or in the lateral faces or in the top face, you can rotate it and take it back to the configuration shown in which you have on the bottom face. But we have to be cautious here. Consider rotation of this cube about the axis that passes through the midpoints of the top and bottom faces. Then rotation of this cube about this axis by 180 degrees will take this A to the other A and the other A will come back to the original A. This will give you the identical configuration, but we should not count it differently. We should be cautious about it. So we will consider only this rotation now, because all the other possible rotations will definitely move the positions of A that we have assumed in the start. So now we fix the A's and allow for only one possible rotation of the cube, that is R. Rotation about the axis joining the midpoints of top and bottom faces by 180 degrees. In how many places can we accommodate these? Well, out of 8 vertices, we have already occupied 2 of them. So remaining 6 vertices. So B can be occupied in 6 choose 2 ways, and that would be 15. Over here, there are 2 possibilities. The 2 B's occur symmetrical with respect to R, the rotation R. If B occurs here and here, in the bottom face, the other 2 vertices, then by performing the rotation R, you're going to get back the same configuration, which means I'm going to count it 1 time. The symmetrical can occur either in this way or along this diagonal, the top face is diagonal. That has two possibilities, either of the diagonal. Only in these configurations, B will remain the same and that will be counted only once. So there are 3 of them. But for the remaining 12 of them, you will have the B's asymmetrical with respect to R. That is, if one B is on the top face, then other B is on the bottom face, that will become B here and B here after the rotation R. This means we have ended up with a different configuration. So we started off like this and we went here. The line segment joining the two B's will now be here. This makes the configuration identical, but we will consider it as distinct if you consider all 12 to be different. Therefore, we are going to divide this by 2, which gives us 6. Because each of the 12 configurations can be rotated and obtained a different one, which is also in those 12. Because asymmetrical will become asymmetrical after you rotate with the rotation R. Alright, now case-wise we will be doing the counts. First case, the two B's are asymmetrical. That is 12 by 2, 6. Now in the 6, there are remaining 4 vertices to place the two C's. Once the C's are placed, we can definitely place D's in the remaining 2 positions, and there is exactly one way for that. So for this we actually have 4 choose 2 ways in order to choose the place for C. But again, we should but now we need not worry about the configuration being overcounted. The reason is that it is already accounted for by this division 2. When you rotate by R, you will definitely get a different configuration because the two B's will be moved to some other asymmetrical B's. So I am going to completely take these 6 ways, and therefore this case would give us 6 possibilities for the two B's times 6 possibilities for the two C's, and the two D's will have 2 choose 2, that's like only one way, which is 36 in number. You can also think of it in the following way: 12 ways not considering the rotation and 6 ways again not considering the rotation, and exactly 2 of them in these 12 times 6 can be paired up, making them equivalent. So dividing by 12 gives us 36 directly. Alright, coming to the next case in which the two B's are placed symmetrical with respect to the rotation R. Suppose, say, without loss of generality, it occurs in the remaining 2 vertices of the bottom face. Alright, if C is now placed symmetric, then it will not yield a different configuration upon the rotation R, and same goes for D. They will also be placed in symmetric because there are 4 symmetric pairs. One is occupied by A, other by B, one more by C, and the one more will be occupied by D. And in the remaining 4 choose 2 ways of placing the C's, that is 6, you will have 2 ways of placing the C's in a symmetrical way, which will be counted as it is, and 4 ways of placing C's asymmetrical. This method of placing C's asymmetrical will now produce different arrangement which is also asymmetrical when rotated by the rotation R. Hence, I have to divide the 4 by 2. So the total would be 4 by 2 plus 2, that is 4 ways. Alright, now let's compute the total. It is case 1 plus case 2. Case 1 is 36. The case 2 will just be 3 ways for placing the two B's symmetrically, and after which you have 2 ways for placing the two C's symmetrically, or 4 by 2 ways for placing the two C's asymmetrically. We divide by 2 just to avoid overcounting. Now this gives us 6 plus 6, that is 12 ways. The total number of ways will be the sum of case 1 plus case 2, that is 36 plus 12, which is 48 ways. So these kind of questions make students imagine what they are trying to do in three-dimensional. So this sort of elicits the students' perspective of 3D and makes them imagine, and even if they are not able to, they can make a cube or think of some object as a cube and do mathematics, which is exactly what we want. We ask students to contemplate about these questions wherever they go, whatever they do, whatever they have, over a period of 14 days, which is one fortnight. We give out solutions after these 14 days at their doorstep. If you are interested in solving such problems, you may apply for a free trial worksheet through www.sumonmath.com. Thank you for watching, everyone. Bye.